Today we're going to talk about solubility, solutions, and polarity. So to begin with, what is a solution? If I were to ask you to describe this cup of yummy looking hot chocolate, how would you describe it? What's it made out of? What's on top? We've got some kind of yummy chocolatey substance covered in whipped cream and sprinkles. So what part of this picture is the solvent? And what part of this picture is the solute? So if we were to describe this, the solvent is the part of the solution that is present in the largest amount. So if that's the case, first of all, the solution is really only this part here. So the solvent then would be whatever component is present in the greatest amount. And in this case, if this is hot chocolate, what do you think that is? Is it chocolate? I wish. But in this case, it would be your water. And what part of this picture is the solute? Now the answer to that could be many things. It could be sugar as a solute, caffeine, cocoa, a little bit of the milk that kind of gets dissolved into the solution. So the solute is the object that is dissolved into the solvent present in the smaller amount. So solution is basically composed of two parts: your solvent, the thing that does the dissolving, and the solute, the thing that is dissolved. And so notice there could be multiple parts of multiple solutes in the solution. So whenever we say like dissolves like, that's an old chemistry expression that can describe so much of chemistry in the world around us. What it means is if something is similar to something else, if a solute is similar to the solvent, then it will be soluble within that compound or within that solution. So for instance, if sugar is similar to water in structure, then it will be able to be dissolved by the water. If it's not similar, it will remain as a precipitant and kind of float in the bottom. So in describing and figuring out if molecules are similar or not, we use the word polarity to describe whether or not things will be soluble within each other. So what do you think it means for a molecule to be polar? Many times I'll get answers that go along the lines of, well, one side's positive, one side's negative. It's like schizophrenic. You're polar. You might be really super nice one minute, next minute not so much. Or you could have split personalities. Okay? And in a way, we are all a little bit of polar. We're not always happy. We're not always sad. We have different moods. Molecules are the same way. Almost no molecule is entirely not polar. But some molecules are a great deal more polar than others. And so we can describe them as kind of how polar they are is how much change in distribution of electrons exist within the molecule. Are all the electrons lined up on one side and the other side is kind of electron sparse? Or are they kind of evenly distributed? And so that's what it means by polar, is an uneven distribution of electrons. So do you think a polar solvent will dissolve a polar or nonpolar solute better? Think about that for a second. If the thing is like dissolves like, a polar solvent will dissolve polar solutes better. Nonpolar solvents will dissolve nonpolar solutes better. Why? Like dissolves like. They're going to dissolve things that have similar polarities to them. And this whole lesson is just going to hopefully increase that understanding of, well, why? Why does sugar dissolve in water? Why does salt dissolve in water? Why do some other compounds like oil not mix with water at all? That's what answers these questions here. So polarity, it describes the dipole moment. It's the uneven distribution of electrons. So by dipole moment, what that means is you can have a partial negative, and that's the calculus symbol for partial. Okay, so really it's like a partial differential equation, but we're not going to worry about that. All it means is we've got a partial negative on one side and a partial positive charge on the other. So whereas oxygen bonded to hydrogen is actually a covalent bond. It's not ionic, but yet the majority of the electrons are going to want to be surrounding the oxygen as compared to the hydrogen. Why? Electronegativity differences. The oxygen's a great deal more electronegative than hydrogen, so it's going to pull a lot more of the electrons toward it. And so that's what's called a dipole moment. So here's kind of the chart to remind you of electronegativities. Fluorine's the highest, down here to cesium is the lowest, being weak. So if you have two elements that are really similar, so for instance carbon and sulfur, they have equivalent electronegativities, so they're not really going to be very polar even if they're bonded together. Whereas if you have fluorine attached to hydrogen, that is a high electronegativity difference, so they're going to have a stronger, they're going to be more polar. So for instance chlorine bonded to chlorine. What do you think, polar or nonpolar? That's right, nonpolar, because their differences in electronegativity is low. So if you were to compare chlorine to chlorine versus chlorine and fluorine, chlorine bonded to fluorine would be a lot more polar. The difference is a lot greater. If you compare sodium and chlorine's electronegativities, that's actually an ionic bond. And so why? Because they have such a great difference in electronegativities that it's almost as if chlorine steals 100% of the electron density and sodium gets none of it. And so that's kind of how we actually can describe covalent bonds. They can either be purely covalent, an example would be like chlorine diatomic molecule, where the electrons are shared almost exactly equally. Or you can have a polar covalent bond, such as hydrogen fluoride, where it's not quite enough to make it ionic, but it is a pretty strong electronegativity difference. And then you got things such as sodium chloride, where there is such an electronegativity difference that the electrons are actually transferred. And so really you can kind of view this as a spectrum of how polar is the bond based on whether or not it's nonpolar to a polar covalent to an ionic bond. Because you can have nonpolar covalents and polar covalents, but then ionic bond is kind of the most extreme of that. The electronegativity difference is so great that it causes the electrons to be transferred from one to the other. Instead of just having the partial positive and negatives, you have an absolute positive and negative. Okay, so here's just kind of an example of this, just kind of viewing in. So what do you think? Carbon dioxide. Now we're going to have to review a little bit of our electron geometries here, because without our electron geometries and our molecular geometries, we can't without a doubt say whether or not something is polar or nonpolar. We'll talk about why in a minute. Okay, so for instance, carbon dioxide, here's the Lewis structure. It is linear. So what do you think? Do you think it's polar? Alright, so there's a couple things to note here. There's polarity of bonds and there's polarity of molecules. I would say that this bond here between carbon and oxygen is polar, but the whole molecule is not polar. Why would I say that? Well, if you cover up one of the oxygens and let's just look at the other bond, between carbon and oxygen, which one's going to pull electrons more? The oxygen is. So your oxygen over here is going to have a partial negative, and your carbon's going to have a partial positive. And your other oxygen is going to have a partial negative. Well, if you have two oxygens on both sides of the carbon and they're pulling in a straight line, this is once again the like pull, like you're having a pulling contest. You're pulling on both sides of a rope. If they're pulling equally and in opposite directions, are they ever going to just pull in one direction? Is somebody ever going to fall in the mud? No, because they're pulling equally and oppositely. So while the bonds may be polar, the molecule itself is nonpolar because of the fact that they cancel out. So if you ever have stuff that will cancel out, it's going to be nonpolar. So carbon dioxide is not polar because the dipoles cancel each other out. If the molecule is not symmetric, then the dipoles will not cancel and the molecule will be polar. This is the reason why you have to be focused on drawing the Lewis structure once again. So it's good to go back through, review your notes from your last couple chapters, and remember how to do Lewis structures. So what you see here, down here, those are called your dipoles, these arrows with the arrowhead on one side and kind of the tail feathers on the other. The way it works is the positive part of the arrow, the part that looks like a positive sign, that's going to be where your partial positive exists. And as it goes toward the arrowhead's going to be where your partial negative exists. So the way I remember it is the end of the arrow looks like a positive sign. So that's why your carbon is partially positive and your oxygens are partially negative. So if you draw the individual dipoles, it has individual bond dipoles, but the molecule itself is nonpolar. Alright, let's look at water. Water has a bent molecular geometry. Remember how it has two lone pairs up here, up next to the oxygen? So what's going to happen here, hydrogen has a lower electronegativity than oxygen, so that's why it's got the positive end being closer to the hydrogen. And it's pointing toward the oxygen. Dipoles always travel the same direction as the bond. So because it's got the bent geometry, you might think if you drew water like this, you might think, oh, well this one's pointing in, this one's pointing in, so those cancel. But the problem is the molecular geometry is not linear, it's bent. And since it's bent, both of these will essentially add together and point it toward where the majority of your negativity is up here above your oxygen, and your partially positive will be both of your hydrogens, and they're not going to cancel. It's as if you were to, oxygen is pulling really hard and they hold out both of its hands in front of them, and some weak people try to hold them still, and the person just wanted to take one step backwards. Oxygen will be able to take a step backwards because it's stronger. It's pulling the electrons more than the sum of both hydrogen combined. And the only reason that that's true is because it has a bent geometry. Okay, so for instance, NH3, its molecular geometry is trigonal planar. It has some electrons right up here. It's also more electronegative than hydrogen, so it has each of the individual dipoles drawn as shown. So if you think about it this way, all of the hydrogens, they're pulling on those electrons, but nitrogen is able to pull so strong, it can pull all of them straight up. Okay, so all of these arrowheads kind of sum together to form one net dipole pointing straight through nitrogen. So so NH3 has the same thing going for it that our previous sample had, our water, is that the net dipole is going to make it so that they don't cancel out. It's going to be polar. So when you're thinking about this, the way to do it is first look at the Lewis structure, decide its molecular geometry, and then look. And if it looks like it's symmetric, they're going to cancel. If it's not symmetric, draw a line right here. Not symmetric. Okay? It's symmetric about this axis, but that doesn't matter. It's this axis that matters because it has to be symmetric along all axes. Okay? If it's symmetric, they can cancel. If it's not symmetric, it's not going to cancel. So it's not going to cancel, so it's polar. Alright, so here's some examples. Linear. If you have two identical polar bonds pulling in opposite directions, the molecule will cancel. Okay, so this was like your CO2, your carbon dioxide. But what if it's like HCN, which we looked at previously? We drew its Lewis structure. Would that cancel? It's linear. It is linear, but hydrogen is less polar, so what you'd actually have is a net dipole moment going this direction. So it's actually going to be polar. So you have to look and say, are the two atoms on both sides, are they equal? Or are they not equal? If they're equal and it's linear, it's going to be symmetric and nonpolar. Okay? Another example, three identical polar bonds from 120 degrees angle each of them. The molecule is nonpolar. Whereas if you have a trigonal pyramidal arrangement, these never cancel. Okay, the molecule is going to be polar. Okay, no symmetry here. Here you have symmetry in all directions. Doesn't matter which way you draw that. Same thing for nonpolar. Symmetry in all directions. Here example, nonpolar. It's got to be polar because you don't have symmetry along this axis. Okay? If you have in this example, you have four objects and they're identical. They're pulling in all four directions. It's going to be symmetric no matter which way you shake it. Okay? This molecule is going to be nonpolar. It's a little hard to see because it tried to draw it three-dimensionally, but if you were to pull out, a model kit and put all four of them equal distance from each other, they're going to balance. So I like to note at the bottom, in all cases where the polar bonds cancel, the bonds are assumed to be identical. If one or more of the bonds are different from each other, the bonds will not cancel. That's the HCN example versus CO2. Okay, so what you're looking for is symmetry here. And why this matters is, once again, you're trying to decide if like dissolves like. So you're trying to decide, is the molecule polar? Because if you have two molecules with equal polarities, they're going to dissolve within each other. Okay, so if you've got two molecules, you threw them into solution together. So in this case, say you've got water and sodium chloride. So here we got water. Whoops. Don't know why I drew that. And here you got sodium chloride down here. That broke apart into sodium and chlorine. The attraction between two solvent molecules is solvent-solvent attraction. Between two solute molecules is a solute-solute attraction. And the molecule attraction between one solvent molecule to a solute molecule is called a solvent-solute attraction. So kind of the idea here is when you have sodium chloride, what literally happens is if you throw a big chunk, a salt crystal, if you throw a salt crystal into water, what instantly happens is the water molecules start to align themselves around the sodium chloride. Because water has a partial positive, its partial positive will want to interact with chlorine's negative, and the partial negative of oxygen will want to interact with sodium's positive. So between those, they'll work really hard because the idea is that the solvent to solute interaction is strong enough to break apart the bond that sodium felt for chlorine. And so by breaking it apart, we're able to solvate it, form this nice big surrounding structure of your forming water and creating a solvent-solute interaction that makes the salt dissolve. So that's what makes it so you don't have giant chunks of salt in your drink. And so this is kind of also the difference between an electrolyte solution and a non-electrolyte solution. If you're able to dissolve ions, so you have individual charged elements floating around in solution, it's called an electrolyte solution. Why? Because it will carry charge. So the idea is if you have pure water, okay, let's say you're bathing somehow in pure water. Don't really know how that's possible, but let's say you are. If somebody were to throw, the whole idea that you throw an iron into or you throw a microwave into the bathtub with you, you wouldn't actually get electrocuted because there is nothing to facilitate the charge transfer of water. Thing is, most water has ions. You've got rust from the pipes, you've got your oils from your skin, not really oils, but just different salts, sweat molecules will get into the water. There's a whole bunch of different ions in water. Your water is not perfectly pure. And so because of that, you can actually run a current through it, so that's why I don't suggest running electricity through your bath water. It will electrocute you. Okay, but if you have a pure water solution with something like sugar, sugar is a non-electrolyte solution. Why? Because even though it dissolves the sugar remains bound together covalently. Because sodium chloride is ionic, sugar is covalently bound together, it's going to stay in sugar clumps, but sugar clumps so small your eye cannot see them. So that's why it's called a non-electrolyte solution, because it doesn't break apart into charges. It just has partial positive and partial negative regions of the covalently bound sugar. So sugar is going to be polar. That's why it dissolves really well in water. Thank goodness, right? Okay. So some common laboratory solvents that you see, here are your polar ones over here. You've got water, acetone, that's typically what's in nail polish remover, methyl alcohol, those are polar. Whereas some common non-polar solvents, hexane, diethyl ether, toluene, a good kind of thing to practice is try and draw out the Lewis structure of all of these. Some of them are more difficult than others. So those are just kind of your common laboratory solvents. Understanding the polarity and drawing the Lewis structure of solvents, and most of the time your main solvent that you have to worry about is water. So if that confuses you, don't worry about it, just worry about water, because water is the most commonly used solvent. So with water, if I were to ask you a question like this, which could you expect to be the least soluble in water? Out of this list of 4, what would you say? Remember, like dissolves like. What I want you to do is pause the video right now and go ahead and try and answer that question. How you answer that question is draw out the Lewis structure for each one of these molecules. So go ahead, give it a try right now. So I hope what you found is CCl4, carbon tetrachloride, has a structure that looks like this. CH3Cl has a structure like this. Here's dihydrogen monosulfide, and here's potassium fluoride. So which of these would be the least soluble in water? Alright, let's start with this one down here. This one's ionic. Are ionic compounds polar? Yes. Hydrogen sulfide. It's not linear, right? It's bent. So if it's bent, is it polar or non-polar? Polar. Okay, what about between these two? Which do you think would be the most polar? This one. Why is this polar? Because you've got 3 similar groups, but then most importantly, one group that is not similar. And so all of these guys would have a positive charged dipoles drawn like this, but this one would be drawn like this. So you actually have a net dipole going out that direction. And with this one, they're all going to want to go like this. And so this one is non-polar. So if you have 3 polar options and one non-polar option, and water's polar, right? Which one would you expect to be least soluble in water? Out of all the polar options, water's polar, so all the polar ones should dissolve in it. So your only option for least soluble is the one that's non-polar. If you had to say which one is the best soluble, I would say dihydrogen monosulfide. Why? Because their structure is the most similar. Similar structure, similar solubility. Okay, so let's look a little bit closer now at these solvent interactions. Okay, we already looked at that one a little bit. So these are the intermolecular forces that attract between 2 different particles, whether it be solvent-solute, solute-solute, or solvent-solvent. Hydrogen bonding, that's one of the strongest intermolecular forces inside of water. So what happens is if you have a hydrogen bond, hydrogen can bond any electronegative element. Most commonly, you've got oxygen. So a hydrogen bond is what you see right here. This kind of dashed line that you see, that's representative of not a real bond, but a force. So intermolecular means between molecules. So not like intra versus inter. Intra means within molecules, inter means between them. So like interstate connects states together. Intrastates are forces that connect within a state. Okay, so intermolecular forces are forces between molecules. So hydrogen bonding is a bond or a force really that happens between hydrogen and an electronegative species of another compound. So that's why water has really strong hydrogen bonding, because of all the hydrogen to oxygen bonds. And we'll talk more about that in great detail later. Ion dipole, so if you have an ion plus water, so for instance if you've got an ionic compound, I think I drew that in here. So if you've got, for instance, potassium chloride, your potassiums are going to be related to your oxygen, by an ion dipole bond. So the idea here is you have an ion and it's interacting via a force to oxygen. So the main requirement here is that you have a polar solvent or solute and an ion that is your solute. Dipole-dipole interaction, that's an interaction that describes a polar compound interacting with another polar compound. So the idea is polar compounds have dipoles, and so if you throw 2 polar compounds into solution, all the positive charges of one compound are going to want to find all the negative poles of another compound. And so they'll line up like that, with a positive lining up with the negative. And you'll have another one over here where you've got your hydrogen, your chlorine, that kind of thing. The last one's probably the most different. This is called a dipole-induced dipole. So you've got one polar compound and another one that's non-polar. So the idea is if you have fluorine attached to fluorine, that's going to be non-polar. But the thing is, if it ever comes near something that's negative, so in this case oxygen has a partial negative charge, as oxygen comes close to the fluorine, these little electrons on fluorine, they're going to want to go, I need to get away, and they're going to kind of push closer to the other fluorine. So what's going to really look like is there's still all of these electrons around it, but they're going to be closer to the other fluorine, and so it's going to be a partial positive charge on one fluorine and a partial negative charge on the other fluorine. And so it's called an induced dipole because it's super quick. It happens like just for a little tiny millisecond. It might even be a microsecond amount of time. And so since it happens so quickly, it's called induced, because originally it doesn't have a dipole, but when it comes in contact with a polar compound in solution, it will have a momentary dipole. So that's the main intermolecular forces that happen. And all of these just happen in solution. That's what causes things to dissolve. That's what causes our sweet tea to taste so good. Okay, so one last kind of thought. We want to think momentarily about the differences in solubility for solids versus gases, because the same rule applies of like dissolves like, but the rules are changed slightly based on whether or not you're talking about solubility of a solid or solubility of a gas. So let me ask the question, what does it mean to be for a solution to be saturated? So we looked at this previously. When it's saturated, that means you can't put anything else in it. Unsaturated, that means you can still add more. So if you like unsweet tea, it's unsaturated because you can still add more sugar. Saturated would be good, wonderful, yummy sweet tea. A super saturated solution would be sort of like if you make tea the correct way, where you heat the tea and while it's still hot you add your sugar, because you can add so much you can almost make it like a syrup, which actually I think that's kind of gross, but some people really like it like that. So the idea of super saturated is use heat or some other means to facilitate an increase in the solute above and beyond what should naturally be allowed to be dissolved in the solution. So supersaturated is like an oversaturated. There's more in it than should be. So, and actually this is how you make like rock candy, is if you take water and you boil it on the stove and you add a whole bunch of sugar to it and you let it dissolve so it's super saturated, then whenever you turn off the heat for your stove and let it come out of boil, all of that extra sugar is going to want to come out of solution. And if you just simply stick like a string or yarn or something into your pot of super saturated sugar water, it's going to crystallize on your rope. And so what's going to happen is all that sugar that was super saturated, that solution wants to turn into a saturated solution. So in order to become saturated, a lot of those crystals will precipitate out onto your rope, and you'll have a normal saturated solution once that solution gets down to room temperature. So if you kind of notice, this is the solubility curves of some typical solids in water. So notice their solubility isn't exact. There's none of them, some of them are perfectly linear, but some of them are not. And so it depends on their size, the charge, but notice the general trend of the hotter the temperature. So you increase temperature, what happens to solubility? It increases. So that's just the general trend of solids. As you increase the temperature, you can increase the solubility, and that means you can dissolve more of it into the solute of water. So what do you think then will happen to the solubility of gases in solution as you increase the temperature? So we just learned that for solids, as you increase temperature, you increase the solubility. Do you think it's the same, the reverse? What do you think? Why? Come up with a real world example. So just pause it, give it a minute, see if you can't think of one. Alright, so the ideas that I've come up with and that students come up with in the past are probably the most simple of you throw a pot of water on the stove and you increase the temperature by turning on the burner. What happens to the gas that's in your water? It boils out. So as you increase the temperature, what happens to the solubility of the gas in your water? It decreases because it's no longer staying in your solution. So as you increase temperature, you're decreasing solubility. And I can't spell. There we go. Alright, so for instance, here's another real world example. Based on what you just learned about solubility of gases, which of these two soft drinks do you think is the hotter of the two? Exact same pop. We pulled one of them out of the fridge and poured it immediately, and the other one was pulled off of the countertop. Which one's which? How do you know? Okay, so if I'm going to ask you, come up with your answer. Is the one on the left hotter, or is the one on the right? The one on the right is hotter. How do you know that? So as you increase temperature, you are decreasing solubility. So this one has more gas that's quickly coming out of solution, and so therefore it has a decreased solubility, so it must have had a higher temperature. And so this is kind of a good life lesson. Maybe you can learn, this one lesson for all of chemistry. This is why you put your drinks in the fridge. If you want them to bubble less when you pour them out, put them in the fridge. Because if you decrease the temperature, you're going to increase the solubility, and that carbonation that makes your pop taste good is going to remain in your drink instead of bubbling out. Alright, so this leads us to Henry's law. Henry's law is basically the idea that the solubility of a gas in a liquid increases with increasing pressure. So if you look at our example on the left, this is low pressure, so notice there aren't nearly as many gas molecules above the liquid, so that means there are not as many gas molecules in the liquid. Whereas the one on the right, there's a whole bunch of gas molecules above the liquid, and so there's a whole bunch of gas molecules below the liquid. So that's Henry's law. Increase gas molecules outside of liquid, increase the pressure, that increases the amount of gas inside the liquid. So why this matters is bottling soft drinks. So for instance, whenever your cans or your pop is shipped, it's typically shipped under pressure. And the reason it's pressurized is because they force a whole bunch of carbon dioxide into your soft drink, which forces the carbon dioxide bubbles into your solution. Whenever you release them, if you shook it up or something, all that gas is going to release, sort of like in this example right here, and it's going to come out really, really quickly along with all of your pop. Okay? So that's one reason too as to why the glass bottles, they say that the pop is going to go flat over a period of time. Whereas if you take like a soda can, aluminum can, it's pretty impermeable to carbon dioxide. So if you leave a aluminum can with a soft drink out for like 10 years or something, you can open it up and it still might be carbonated. Whereas a glass bottle, 10 years later, it's not going to be as carbonated because the carbon dioxide can actually slowly escape out the glass. And so that's one reason they switched over to cans. But that's another story. Okay, but the idea is they must ship it under pressure. And that pressure forces all of these bubbles down into it. And so the idea is you have temperature that can relate solubility. So as you increase temperature, you're decreasing the solubility of gases, but as you increase the pressure of gases, you're increasing the solubility. Okay, so if I were to ask a question, who wants to open this can of pop for me? Shake it up. Shh. You want to open it up? Not really. So why and how could you eliminate some of this explosion? And why does it work? Okay, so for instance, a lot of people say if you just tap the top, it's going to work. But actuality, what's in the top of that can? Top of the can is air. And the bottom of the part has your soda mixed with your carbon dioxide. Okay, so if you tap the top of it, you're not doing anything. You're just simply mixing around the air pocket. But if you maybe tap along the sides, if there is any CO2 with so much energy it wants to escape, when you tap the sides, it's going to join the air pocket. So now those carbon dioxide molecules that have so much energy because you shook it, they're going to come out, but this time they're going to come out with air instead of with your soft drink. And so that's why if you tap the sides, it might do a little bit of good, depends on how good you shook it. But if you tap the top, it's not going to do anything. Okay, so to kind of recap today's lesson, like dissolves like. You have to use Lewis structures of compounds to determine solubility. Polarity is the uneven distribution of electrons. And dipoles can show you how the electrons are distributed. So you really need to look at symmetry based on the Lewis structure and decide whether or not bonds are polar and whether or not that leads to the molecule itself being polar. Compounds can also interact in solution via intermolecular forces. So with that, we're talking about the hydrogen bonding, the dipole-dipole bonding, the dipole-ion bonding, and the dipole-induced dipole bonding. Solubility of solids increases with an increase in temperature, whereas solubility of gases decrease with an increase in temperature. Additionally, solubility of gases increases with an increase in pressure.